All right, so our final lecture will be your RAM, which is random access memory. So let's go ahead and get into it. All right, so the announcements is pretty commonplace. We've seen all this stuff before. So we'll go ahead and skip over that. But this is going to talk about that last chunk of the project that we work on, right? So hopefully exciting. Now, as a review, everybody, we've built the ALU, the brains of the operation. Now we need a few more things to take this from just a calculator circuit to an actual computer. Now I know I keep repeating this every week, but I do want to drill it into everybody's head that this is kind of the track that we're taking, right? So we've come up with ways to store programs, interpret those programs, execute those programs, and in fact, we now need to store data for those programs while they're executing. So that's a little magic bit, and the best part is that we have kind of already done that with that huge spiel about the program counter I went on last week, right? The program counter itself is a register, right? And you actually saw an analog to that when we were working with the Project 5, right? Again, the PC program counter is a register, just like every other, I guess, register. Stores a value, you can add and subtract from it, that sort of thing, and you can reliably pull from it and interpret it as you will. So that's exciting news for us because I think we can just use that and scale that out to a bunch of different registers that'll effectively serve as our memory, right? So the deal is here that we are going to build that fourth bullet point, right? That is what we'll be creating. So again, just a quick review. The project numbers are a little, they might be off here. Actually, no, they look just about right. Um, and today we'll kind of be talking about ways to store data for these programs using registers of RAM, right? I'm going to take this moment to ask, is anybody perhaps a little lost on these top four bullet points? Considering this is our last conceptual lecture, does anybody need like a re-explanation of something like that? And no worries, feel free to hop in at any time, okay? All right, considering that we are good to go on these bits, let's talk a little bit about Project 7. Using registers of RAM, right? And again, Project 6 is our current, that's the one that we're on right now, that we'll be working on, right? So again, any questions with that, go ahead and send them in the Discord. We could probably do something where we make like a channel for each project's questions. That might be
That
cool.
worked well for Project 5, so probably do the same thing for 6 and 7.
Cool, that makes sense. Because the messages are kind of falling into my general Discord inbox, which sucks because it like doesn't stack well with like my other stuff, so I keep missing people's messages. So a dedicated channel I think would be excellent because we could just go in and answer questions. So I think let's do that for Project 6 questions. Um,
Also, just a note, I got a couple email messages. If you can, please do try to message me on Discord. I will get back to you the fastest. I don't like for some reason over the past few months, my email has just turned into an utter spam box, and so I don't really check it as much.
Ditto, but I think so if Ashwath can't grab the emails, I can grab them. So make sure to CC me on those. I think I've already gotten some emails and I'm CC'd, so I'm due to my complications of being employed by Mr. Larry Herman, I am mandated to check my inbox twice a day, so I will see your email. So grab Oswath on Discord or just shoot me an email, and that should be probably the quickest ways to reach both of us. But I think we'll also throw up a Project 6 questions channel, and that'll be the end all for Project 6 questions. So very exciting stuff. Hopefully that should be helpful. Right on. Let's move forward here. And delve into our random access memory, right? So we all know what random access memory is because the laptop or desktop that you're using has advertised some ridiculous amount of memory compared to what we'll be building. 4 gigabytes, 8 gigabytes, 16, 24, what have you, right? We have to think about what that actually is, right? So does anybody kind of have an idea of what RAM is, what RAM does? You can just throw it in the chat. Anything, right? Any semblance of an understanding of RAM. Solid tough crowd. At the end of the day, right? RAM is kind of essentially. Oh wait, actually, maybe I'm looking at the wrong channel.
Nope, tough crowd indeed.
Tough crowd indeed. All right. Um, but basically, RAM itself is just memory that's floating around, attached to your computer, the key is it's kind of volatile, right? We can add from it, remove from it, and usually we keep it here as like fast access memory, right? So let's, for those of you who have already delved into computer architecture taken 411, let's forget about the cache um, for now, right? Let's just think of RAM as that most close layer to the program in terms of storing and retrieving memory, right? Specifically, if say our program has to be keeping track of a register, right? Like registers 2, 3, 4, etc. Um, those are going to be represented by random access memory. The reason being, we can edit those whenever we please, and we can pull the values of those fairly quickly, right? Now, on actual computer systems, there's a bunch of varying memory, with cache being the fastest, RAM being the second fastest, and disk being like the worst. I mean, there's a lot more layers of memory, but I feel like I'm leaving out cache here, so that's something that people have taken 411 might be upset about. Um, but this is indeed the model that we're going with, right? Um, so us, particularly for our computer, we are a few things. We are not going to take the time to actually write a disk because, I mean, for us, there's really no technological difference between writing to RAM and disk, right? We just need memory in general that can store something and can be edited. So in our case, there's only really one way to build that at a very low level in Minecraft. So we can just stick with building our, regular memory, and that serves as our RAM, right? But the reason on computers that they do such a thing is because um, we live in a material world, and some memories just harder and more expensive to create than others, right? So generally, what's on disk will be like the cheaper technology of the era, right? Or just the slower, higher capacity technology of the era. It went from hard disk to SSD to NVMe SSD, right? Which is kind of getting closer to how RAM sticks maybe would be, but our RAM has always been like flash memory, DDR, um, so much faster, but perhaps more expensive, um, and requires power to keep on that sort of business. So a little bit of a comparison there, but I just wanted to clarify that essentially I would say the best analogy here would be that our disk would be our ROM, right? So that's the stuff that we go in and manually change ourselves, like the program files, right? And then the RAM itself would be like these registers that we have going. So at the end of the day, we do need fast access modifiable memory that we can use to store the values that we create. And incidentally, here we call that RAM, which is not so far off from the computing analog of that. So hopefully that makes sense. Kind of a little digression there. Um, so let's think of it in terms of the stuff we've built already, right? While our interpreter circuit, which we have not yet actually built, is actually executing that code, where will it store the values that it calculates, right? Now, this is important for us, especially for those of you who've kind of really gotten into the depth of Project 5, right? Because we understand that while we're performing an algorithm or something, or computing some meaningful value, we need to make sure we keep track of those values that we create. And most of the time, they are paramount to the completion of the algorithm itself. Um, Now, really, we're just thinking of registers here, right? So if you do need a refresher on where registers are, just think back to 216 in assembly, right? And at the end of the day, just like I said, when I was going on my spiel in the previous slide, these requirements are pretty much filled out by RAM, right? Um, so first, we're going to take a look at the concept of RAM as a whole. Then we're going to figure out why it really is the perfect choice for us here. And finally, we'll talk about implementing this business in Minecraft. And again, by RAM, really we're just considering these sort of registers where we can store values, right? Just fancy latches is really what we're looking at. So hopefully that'll make a little more sense as we keep moving forward. But let's take a look at what we're building here, right? Program counter, this is good stuff. This is your next project. You'll finish this up, right? And then this will interact properly with our ROM and keep providing it sequentially the number of the line that we're at, right? Um, and keep spitting that out to the circuitry to interpret the actual code, right? Which will in turn interact with the registers, kind of change the variables, mess with them a little bit, and perhaps put a proper return value in a certain register, um, and then kind of execute that algorithm. So that's good to know, and we have that up our sleeves. Let's talk about RAM as a concept. So, it is known as random access memory, and it is the quickest memory in the computer that we can pull from and write to. Again, let's forget about cache for now. This is kind of just where we're at. If you want more, take 411. As such, this is a computer architecture structure that we're deciding our computers, that our programs will be reading and writing to, reliably and quickly while they execute. Right. So I mean, I keep rapping on this point, but it just about is um, exactly what we say it is. Right. Um, you know. So hopefully that makes sense. And again, feel free to stop me whenever if this is not making any sense. Okay. But let's keep in mind that we're not actually just making this stuff up. We're following a general recipe for a computer, right? We'll talk about this in like I say final lecture, but probably we'll just kind of throw bits and bobs out there as we kind of office hours everybody and get them towards building the final project. Um, and in our case, RAM and registers will be used interchangeably, right? That's the most important thing about this lecture, right? You kind of know comp arc already. You'll kind of think of RAM as one thing, but here we're just going to think of RAM as our registers, right? Volatile memory that we can access quickly, as opposed to read-only memory. Um, so bending the definition a little, but it is a one-credit class. So what do the computer gods say about how we should actually build our RAM, right? Here's the dealio. We need volatility, which means RAM is only useful when the circuit is powered on, and it will lose all data is storing when the computer powers off, right? This is very neat, right? So in other words, RAM is not where you should store something that you need the next time you boot the computer, perhaps even like the next time you open something up, right? Well, actually, that's not true. But let's think of it that way, right? It's kind of just what we need for like one run of the program, I would say, if we're going to abstract this concept, right? In other words, if you have like some system settings or something, or some deeply set lower level flags, you do not want them placed in the RAM. That's not the stuff we're going for. Also, we want access equality, right? So it takes the same amount of time to access any address of RAM. Um, Now you might be like, well, that sounds a little weird, especially if we have linear memory addresses, right? But think of it this way. Um, the access time of like a hash table, for example, right? That is amortized constant time. And we're kind of looking at the same deal here for our RAM, right? As long as you know which address to pull from, you're getting that in constant time. So that's where the access equality comes from for us here, right? Um, we don't want maybe like to take a lot more time to pull from, I don't know, address 300 than we do to pull from address 0. Um, and of course, you might be wondering, okay, well, this clearly is dependent on the actual distance, right? Um, that it that we literally build our circuits on, right? So in other words, a memory address that's physically much closer to us, Minecraft-wise, is much faster than an address that's like very far from us, like 600, 700 blocks away, right? Obviously, we'll never build anything that big in this class. But it is a little weird to think about me talking about access equality and seeing this. Um, so it is what it is. But in general, the idea is that we want access equality when we're building our RAM structure, right? Think of this in terms of like perhaps the almost a data structure that we're using to store this stuff, and not the actual physical structure, literally, especially in this class. So how do we achieve such access equality? Well, it's quite simple. We leverage the mux and demux combination so we can access one of hundreds, thousands, or even more memory addresses in a cluster of RAM, right? We did talk about this, by the way. In a previous lecture, we did talk about how your computer would look very spaghetti if we didn't have mux and demux. Um, so this is kind of where we're getting at that, right? So in other words, we will use a small version of a mux and demux to make sure that we can pull data from whichever register that we please, right? By minimizing the wires that we use to reach to them. So that's the exciting bit here, and you'll definitely see like a RAM cluster, and then kind of figure out how to implement that mux and demux. But again, I just want to specify that you all have come so far, and you know the very basic circuits to build a computer. If you were given enough like bricks and blocks and wires and such and resistors, whatever, you could probably put together a very simple digital computing circuit just using the stuff that you've picked up in this class. And I personally think that's beautiful. Right on. More conceptual stuff. I suppose you don't really need to know this, but I guess just cool things to throw out there. There are two types of RAM in the computer world: static RAM and dynamic RAM. Right. Static RAM is just a bunch of circuits, and dynamic RAM is circuits plus a capacitor. Um, SRAM is generally faster than DRAM, which is why it's mainly employed in your cache, right? So on your processor itself. Um, Now DRAM takes up less space, though. It sounds counterintuitive because it has an added capacitor, but it turns out that the dynamic RAM, right, has much smaller circuits, so it is what it is. But it's true, right? So since it's smaller, we can smoosh more into one place, and we don't really value speed as much as the cache. We use DRAM in the actual RAM chips on our computers, and SRAM within our like cache and our processor, right? Um, in our case, we are going to be using the equivalent of static RAM that we can just pull from all the time because Minecraft is excellent and doesn't have all this electricity business that we have to deal with. As such, we don't really need to deal with capacitors, and we can focus on the actual logic portion. All right. So let's go ahead and move on here. Oh, whoopsie, I clicked the wrong thing. Very nice. Okay. In 389E, we don't have to worry about silly things like power consumption or storage bandwidth because our computer is about as smart as a saguaro cactus. That is not like it's not an abstraction or anything. I literally am just saying it has like the compute power of like a house plant, right? It is not a very smart computer. Now it can do some stuff. It can add some numbers, maybe do some exponentiation if it's really feeling it, um, but really not much more, right? So we don't really need to worry about differentiating between RAM or even building a cache. Why? Because we don't. At the end of the day, we don't really need it to be that fast, right? So hopefully that makes sense to everybody. I talk about all this RAM and cache and all this business, right? But we just need a reliable way to store and pull data, right? So we're not gonna go nuts with any SRAM, DRAM, cache, business like that. And hopefully this makes sense. That's the point I wanted to kind of hammer home with this. Um, so I'll take questions if anybody's got any. Cool stuff, cool stuff. All right, we'll keep going. Here's that RAM when looking at a computer, right? So as we go over this, I want you to try and think back to the components that you already know, right? And try to compare them back and forth between the digital logic components you learned about already. And the hint is you actually know literally everything that you need to know how to build. This right here. And I wanted to include this diagram here, not because it's what you'll be building, but this is how, a more complex RAM circuit would be built, right? And you'll notice that we've got actually muxes here coming in from both sides, right? Doing a sort of coordinate select. This is a very cool way of doing it. Um, uh, and in fact, we'll kind of be exploring a very similar way to build random access memory. But it's neat how something like this works because essentially you're cutting down access time by providing two coordinates, right? And in turn, you're getting, for the power of n select wires on each side, you're getting 2 to the power of n times 2 to the power of m, or so like, I guess m or n, these could be different, right? But this is a ridiculously large number, right? If everybody can see this. Um, right? So this right here is a ridiculously large number. So I just want to like emphasize the magnitude that you can achieve by just screwing around with a few multiplexers, right? So let's assume just, I don't know, for the hell of it, this is, I don't know, 5. Yeah, we could just call it 5. And again, think of it this way, right? 5 wires, that's absolutely tiny, especially when you're building like an architecture yourself, right? Um, and that is pretty crazy. The thing is, when we multiply this, right, so we increase this by certain magnitudes, we can get even bigger. So let's say, suppose here on this multiplexer, right, and again, we all know how multiplexers work, hopefully, so this should make sense, but think of it this way. Column select, we basically think of that as a multiplexer, right? So hopefully that all makes sense to everybody. Let's say that m equals 10, right, and just to kind of demonstrate just how, like, massive this sort of thing could get, our result would be, right, 2 to the power of a 5, 2 to the, sorry, I just, my mouse is 2 to the power of 5 times, oh lord, I'm gonna look for a text tool 1 sec. Okay, no, we don't have a text tool, that's fine. uh, okay, 2 to the power of 5 times 2 to the power of 10. Okay, so it's still legible, hopefully. There we go. All right, now coming out here, right, so we know this is 32. Oh dear. Times, and again, this is just 32 to the power of 3, so hopefully, think about how monumental this number has become, right? We're going from 5 wires on this side and 10 wires on this side to 32 times 32 times 32. Hopefully I did my math right there. But regardless, it is just absolutely humongous the amount of values that we can interact with, store, all that business, should we feel the need to if we're using a model like this. So again, super cool stuff. And you know everything you need to build this, right? So we can talk a little bit about the components we have here. Um, why not? We have, over here, we got our multiplexer, right? Oh, there we go. That's a little easier. We got our mux over here, right? Um, and in here, all we really need to do is talk about, each of these individual bits here. We could just have like latches, right? Because at the end of the day, we're just going to be sending like a signal in that says, hey, I need to be able to write to you for like a split second, right? And then we send another signal that's either set or reset, right? So again, hopefully, you all remember that bit from what we talked about earlier. But that's really all we need to be doing. So this kind of allows us to activate one of these, right? And then what we can do is we can just send a uh, signal straight up to like all of them and say, okay, whoever the mux is saying turn on, so the mux will tell this dude right here, he'll tell him, okay, you need to be able to change right now, right? Then we can just pulse this circuit with like some data, either a 1 or a 0, and we can say, okay, well, you need to be set or you need to be reset. Um, and that kind of tells us where we are. So any questions on that? Awesome. All right, awesome. So we will move on. Cool, 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 cool. Boop. All right. Now, we're going to talk about RAM as an idea in Minecraft. Now, this is the exciting stuff, everybody. This is where we're going to bridge the gap between that stuff sitting around in your computer and this cool bean stuff that we'll be building in this class. So, previously on CMSC389E, you worked with ROM, which was read-only. You've also seen the background for basic latches, right? And remember, latches are just flip-flops that we throw a little bit of special stuff on, just to make them a little easier to read and write from and enable, right? So look back to the memory lecture if you need a refresher. And honestly, I think I'm going to pull up the memory lecture because I think that it is just somewhat useful. Zoop. I lied. It is not this lecture. It is week 8. Oop. Ah, okay, awesome. This is what we're talking about, right? Um, that is, ta-da, this bit right here. We have a control wire right here, and we have set and reset, right? And at the end of the day, this little construct, this whole thing tells us whether set or reset, whether Q is on or Q is off, right? So 1 or 0, right? We're still missing a few pieces of the puzzle here. You might be thinking, well, we need a way to store the memory, right? Um, but this latch business, it only stores a 1 or a 0. That's not very sufficient for us in terms of actual registers, right? That's a pretty pitiful register if it can only store 1 or 0. So here's our dealio. We're going to actually put a few of these latches together to make a very awesome storage. So think of this way. We're tackling, as a further explanation of the consistent value of storage, a beautiful combination of the last two projects that we're working on, right? So we're going to store data in a similar way to what you've seen in the ROM, right? In that sense, using a cool decoder-based technique to read from it. However, instead of just using torches, we're going to be using a set of latches in an intelligent way, right? In order to read and write data. And I know I didn't put read here, but essentially it's that, right? So think of it this way. That project where we had all the, well, I mean, we will be, I suppose, having all the torches uh, on a redstone decoder sort of business, right? Now we will be, instead of those torches, putting down latches, like series of latches that'll help us kind of pull certain values from those registers. So hopefully that makes sense. Now, before, you essentially created a singular register that could be added and subtracted to, subtracted from for every cycle. Now our goal is to do two things. Number one, let's take that circuit, right, and remove any extraneous bits, right? I know our program counter comes with a few extra doodads. We have a little, I guess, pulse limiter, things like that, right? But we just need to take that one register that stores our line value and replicate it over and over again, right? So cut that down to a more compact, modular form, because at the end of the day, we want to fit a bunch of sticks of RAM together. So we're going to kind of moosh that into a cool little compacted version of it, right? And then put a bunch of those dudes together. So you can basically store all of your registers in one big sideways sandwich, right? Just a bunch of them all together, stacked up like dominoes, kind of. Not sure how else to. Maybe like cheese in like one of those deli cheese bags. Basically just adjacent to each other, right? So let's synthesize this information into an actionable set of requirements. Now we need a circuit that stores data for us that we can easily write to and read from. That's one thing. We need to be able to access all the numerous addresses in that circuit as efficiently as possible. That's another thing. And finally, we want to request an address in binary. Request and address in binary and be able to perform a read-write operation on that particular register, right? So we want to be able to like request or even just like write to do anything else with certain locations um, using an address in binary, right? So we could say at memory address 4, um, turn that register to, I don't know, 5, right? You could totally do that. And we want to be able to do that as efficiently as possible. So let's take a moment to think about which components we need. And we've got, 3 here that we can, I was trying to draw stars, but just imagine that they are. Because these are the 3 things that we really need to look into. Or, right, okay, these two things. I don't know why I highlighted the top thing there. Zoop. So for this one, that should be fairly simple. We talked a little bit about latches, right? Um, and again, for this one, we really are only thinking about, again, technique to get all these numerous addresses. Remember, the key here is we don't need to access more than one of these registers at once, right? Which is solid, but we don't really need to be accessing anything else than that. So we can totally get away with using a mux here, right? Because remember, if we have a bunch of, let's clear the rest of this stuff. I really want to emphasize why we can just so easily throw on a mux here without losing anything. If we have a bunch of memory addresses like this, so just picture that all of these little squares are latches, right? Like series of latches and stuff like that. We only need to access, we're getting a little signal here coming in. We only need to access one of these at once, right? We don't have a very sophisticated if we were to write a parallel Minecraft processing architecture, which sounds ridiculous, but it's totally doable. You just need more like lines of code executing at the same time and reading and writing from the same memory. And the key there is you'd be editing the registers, the same registers for all of this code, right? So you need to build in a way to have perhaps, I don't know, some other structure that lets you. I guess you wouldn't even be able to use a mux. You'd have to use some sort of weird double mux coming in. Yeah, that's what you'd have to do. Like 2 muxes on top of each other to read from the same set of memory, but then you wouldn't be guaranteed to not have race conditions. So again, very strange. But the point is, for us, we don't really need to be looking at more than um, like 2 memory addresses at once, right? Um, and that totally works for us, right? So at the end of the day, we're pulling like data from a certain part of this mux, and then we're pulling, maybe data from another part of this, but we're never going to have stuff that accesses this at the same time as us, so we really don't need to worry about it, right? In other words, data race, impossible with us. So hopefully that makes sense. In that sense, it should be very easy to say, okay, well, I mean, I'll just mux it and take whatever I mux over to, right? So if I get asked to go to register 3, then my mux will just send me there using the select wire. So again, here's the stuff that we've talked about in class, right? And it's really not that much, but we've learned all of it thus far. And here, in fact, the reason this is the last project is because we use just about all of this stuff, right, to really put together a RAM circuit. These registers here are the most complex thing we'll be building in this class. And implementation details, I just like to talk about a little bit. So how will we implement something like this? Well, we'll be using SRAM, no need for capacitor here, and this thing called a D flip-flop, right? That's just an augmented version of the SR flip-flops you learned about earlier, right? Um, so they just had a little bit more of a neat construct here, such that we can just throw in the data right off the bat, given that the clock right here is saying, okay, you're good to write to it, so we can write in data no matter what. And it's cool because in here, if you get a nothing signal coming in, right, it'll actually get inverted and get sent to this reset. So if we have nothing coming in, as a matter of fact, um, this flip flop will say, oh, well, if you are enabling this write flag here, right, so this clock, right, if you're basically saying, hey, register, guess what, I'm going to write to you, and then you don't actually send it any signals, it will automatically flop back over to a reset state, right? And that's what differentiates this from our other flip-flop. So again, if this dude is on and says, hey, guess what, I'm going to write to you, my guy, um, and then in data, you say, well, I'm not actually giving you anything, um, then tough stuff, right? If you've enabled a write flag and you're not giving it any data, it's going to say, okay, well, nothing's going in here, so this set flag is going to be off. But then coming down here, this inverter is going to say, whoop, I got to give him something. So then something will come through the reset, and it'll go in and perform that whole latch business, eventually turning um, this Q bar to on, right? Which basically signifies that the data is set to 0. So hopefully that makes sense, right? That's the reason we're using D flip-flops here. Throwing in this little inverter just makes it so easy for us to set and reset. Again, didn't throw this in the previous lecture just because it's kind of unnecessary when you're learning about the concept, but now when we're actually applying it, it makes total sense. So hopefully that makes sense. Moving on, it's basically just your old flip-flop with an added special feature. We're just making sure the same signal isn't fed in from both S and R, right? Which is also another added benefit. Here, we can't like send in two signals and make some horrible mess of the whole situation. Again, our circuit wouldn't be designed to do that anyway, but just another way to protect from that condition. And if this is very confusing for you, you'll build it, but just understand that's a very cool way to use flip-flops to store data, right? So that's kind of the bottom line here. It's cool and it's safer than our previous latch, so why wouldn't we use it, right? So just like before, each flip-flop, this business right here, can be seen as one bit of memory, right? That is, each of these fancy circuits can store either a 1 or a 0. We're going to need a lot more of these. So let's assume that we now have a ton of these dudes all laid out in some sort of array or matrix. Again, how would we be able to access the ones we want? And remember, we talked about efficient memory addressing in a previous lecture. We've kind of been over this. I feel like a lot of this presentation is just me repeating myself. So it is a multiplexer, right? Mux and demux. Um, so to get the address we want, we'll use a demux, and we're going to use an array for simplicity's sake here, right? We could totally use a matrix, but an array is just like a much more simple way to pull from this, and that's what you're going to be doing in your project. Um, and this is a very cool reason we want to build these RAM blocks in order, right? That is, what if we want to pull more than just a singular bit from RAM, right? And this is kind of interesting. I know I said bit, but let's talk about a singular block of RAM, right? Suppose we want to pull a massive value that takes us 3 RAM registers to store, right? If we build in order, if we maintain an order of these RAM addresses, right, we can do something like that. And that's how these more advanced computer programs work, right? So again, we're not like, this is kind of an aside here, right? But if your block size is 4 and you want to pull the block starting at n, all you need to do is say, hey, computer, give me the block starting at n, right? Computer will be like, bet, I'll give you RAM block n, I'll give you RAM block n plus 1, n plus 2, and for free, I'll throw in n plus 3, right? And that's how you store, you retrieve a much larger value from RAM that could be limited in size or memory address blocks, right? So it's an interesting way to do this. I use the word block size again liberally. It's used to mean different things, but I just want to hammer this home because I feel like maybe Larry might use something similar. I know he does talk about his like heap diagrams in like an interesting way, so this is kind of a similar way of abstracting it. But hopefully this makes sense, right? Think of it this way: if you had all your RAM floating around in a machine arbitrarily, um, right? If you had address 1 all the way on the left side of your computer and address 2 all the way on the right side of your computer, if somebody wants a value that's stored sequentially, like maybe a number that overflows into address 2, right? And if they want to get 1 and 2, that's going to be a huge pain. right? But if we store them in order, in some ordered form, um, it's super easy to amortized constantly pull a block from your RAM, right? Whereas if you had these floating around in different locations, we would not be guaranteed amortized constant pull time just because you wouldn't know where address number 2 is reliably if you knew where address number 1 is, that sort of thing. Um, so again, just some food for thought. I mean, maybe there are ways to make what I said just worked with like a weird hash table in your mux, right? But that don't think of it that way. That's just making a problem where there doesn't need to be a problem. Um, but yes, in other words, there is a reason we keep these fellows in order. So we're straying a little bit from real world architecture, sure, but don't forget this is still a game, right? And the best part is we don't have to concern ourselves with the nuances of electronics, and nor do we have the spatial limitations of the real world, right? What we do have, though, is limited time and workload expectation. So that's what we're forced to work with. So we're trying to make this RAM business as easy as possible, right? So TLDR, we made things easier, making certain architectural choices. You are still building a functional computer in this class, but it is a very simple one, right? So, one credit class, it is what it is, right? It is a computer. Um, so hopefully that shed some light on stuff. And again, the reason I kind of hope maybe rushed this a little bit is because we will be around the next few weeks to kind of conceptually maybe go over this stuff, provide office hours help, and really help you understand these points as you round out your final. I mean, I say final project, but as you round out your completed products for this class. Um, so awesome. That's what we have. We are going to talk a little bit about the final project later, not this week, um, but not to worry. That is due to come in the future. But right now, I'll hand it off. Oswald, if you have anything to throw in, feel free.
Yeah, so the project that this material goes with, the RAM, is the final project, or not the final, like the last project before the actual final project. Um, and it's not hard as much as it's tedious. It's not like yeah, it's not difficult per se, but it just requires a lot of like clone and keeping track of what block is where. So it'll be released like after Project 6. We still have one project in between, but just keep it in mind down the pipeline.
Perfect. Awesome. That is excellent advice, Oswald. And I think that's just about, I feel like all we've got. I'm going to go ahead and